Alright, welcome. So in today's video we're going to go over the derivation of the G sub k equation for low-pass Butterworth filters. Now in case you've never seen this equation, it looks exactly like this, and it's used in the design process for these low-pass Butterworth filters that we see right here. So inside this filter here, you have k elements where the kth element is either an inductor or capacitor. And you can actually use either design, the one on the left or the one on the right, where the difference is the first element here is a capacitor, the first element here is an inductor. Alright, so now that we know a little bit about these ladder circuits and how to use this G sub k equation, let's just go right into the derivation. Alright, so the very first thing we want to think about is what sort of constraints we have on this circuit. And there's really only one main constraint, being that the capacitive impedances and the inductive impedances, they all must cancel out. What this will do is it will cause essentially our whole filter between the source generator and the load to have a imaginary impedance of almost zero. So it will lie almost entirely on a real line. If you were to graph it on a Smith chart, it would lie here on this real line. And again, doing this makes the circuit matched, and it will provide us with essentially a Butterworth filter. Alright, so how can we write this formally? Well, if you notice that if we go with the configuration on the left, all the even components are capacitors, and all the odd components are inductors. If you go with the other design, it's exactly the opposite that's true. Needless to say, we can write out mathematically that the sum over the even components of G sub k must be equal to the sum over the odd components of G sub k. So this is going to realize our constraint, and now we just need to find whatever this function G sub k will be for some periodic function. Alright, so for our periodic function, let's just choose a sine equation. Okay, now we're going to rewrite G sub k. Instead of having a 2 here, we'll put an a for some sort of amplitude. We'll have our sine equation, and then our interior function f sub k, which will really be the thing that is calculating all of it's doing most of the work for our G sub k elements. We have to take it and scale it by pi so that we fix it to the unit circle, and we have to normalize it to n, the number of elements. Alright, so if you look at what we wrote up here and we choose n equals 3, well, what we'll have for the even components is G sub 2 will be equal to the odd components, G sub 1 plus G sub 3. So now we will substitute in our G sub k equation that we wrote here into this equation. And so what we'll be left with is this row. Alright, now what we can do is divide by a on everything, take the sine inverse of everything, and then we have this common factor of pi over n that can come out. And so what we're left with is our interior functions evaluated at the indices that we had mentioned earlier. So you're left with this function we got here from here, pretty much. Alright, now at this point, we just need to find this interior function. And I believe there will be an infinite number of solutions. So let's choose a simple one. And we'll say that it's a linear function. F of k is going to be equal to some constant times k plus some other constant. Alright, so at this point, we need to make another realization. And that realization is that inside this gray equation right here, we have to notice that, this is the G1 element and the G3 element here. We have to realize that the G1 element and the G2 element are shifted by pi halves. And so if we graph that on a unit circle, it looks something like this. So perhaps we'd have g sub 2 here at maybe pi third. And maybe this is g1 here at pi sixth. So if we want to get the addition of g1 and g3 to be equal to g2, that means that we have to shift g3 pi halves over from g1. So we'll end up with 5 pi 6. Now what this will do is it will allow the y components from the sign value to be exactly equal to g sub 2. And so really what's going on here is that we can write out f sub k equals 2 is equal to f sub k equals 1 plus f sub k equals 3, and we can also extend this and write it's really just equal to f of k evaluated at 1 plus f of k evaluated at 2, or sorry, evaluated at 3. Made a couple mistakes there. F sub k evaluated at 1 plus 1/2. And really you can think of this as being the pi halves, but we pulled the pi out everywhere, so we're just left with a 1/2. Alright, and my bad, there should also be a 2 right here in our equation. So just bringing that down, we can add up these two f sub k's. Okay, so now that we have, our base equation for f of k, and we have this realization that, oops, I made a couple mistakes there, but we have this realization that the third element is going to be shifted pi halves away from the first element. Well, now we can go and plug in our equation, and we end up with this. And you can do some algebra, and what you'll find is that C2 is equal to negative 1/2 when you do this. So at this point, we have our C2 value, but we cannot get C1 unless we have another data point. And so in order to find the other data point, what we'll do is we'll use the n equals 1 data point. Now there's two ways to proceed from here. The first way is kind of cheating. It's to go up here and look at this equation, plug in n equals 1 and k equals 1, and what you'll find if you do this, that for n equals 1, g sub 1 equals 2. Or really what's happening is this whole argument goes to pi halves, so that the sine function is evaluated as 1. Now this is sort of cheating though, so let's look at the I guess scientific reasoning behind why this is. So at the n equals 1 data point, what we really have for our circuit is this filter over here, where we just have a resistor, an inductor, and then the load resistance or impedance. Now, if we want everything to make sense with what we're doing here, we need this G1 value to be equal to 1. Now, what that's going to do is it's going to mean that our impedance, so let me write this out, if G1 equals 1, then after denormalization, what we'll be left with is just the inductor value here, or sorry, just the impedance of this inductor. Or if we went with a capacitor as our first element, we'd be left with just the impedance value of our capacitor. And so that's why this is kind of an important step in the whole process, to realize that G1 equals 1, and if you make this realization, you can go through and do the algebra to calculate that C1 will also be equal to 1. Now, you'll notice there's one thing that we kind of neglected to talk about, however, is the value of A here. Alright, so in the actual equation that is used in all the textbooks and tables, A equals 2. Now you'll notice we could conceivably select any value for A, and for larger values of A, so the limit as A goes to infinity, we'll see that our G sub k elements will also go to infinity. Now what this is going to do is it's going to just increase the impedance of all the various elements in our filter or our transmission line, however you look at it. And it's going to give us this end effect where if we go and graph the frequency response of our filter in dB, at the low frequencies, normally it's going to pass almost all of it and then attenuate heavily at higher frequencies. And so this is for the A equals 2 scenario. Now, if we go in and select something else, say A equals, I don't know, A equals 7, it's just going to attenuate this even further. And so we'll have even more loss, and it will probably look something like this. So that's for the A equals 7. Alright, so I believe this pretty much wraps it up. This is the derivation for the G sub k equation used in low-pass Butterworth filters.